Okay, we're going to go over power functions in section 2.2. In section 2.1, we talked about polynomials and quadratics. A power function could be quadratic or some sort of polynomial, linear even, but what's important is that it only has one term. But really, the power could be anything. Okay, a is the power, and it could be anything. It could be any real number. K is the constant of variation. And don't get too hung up on the use of K or A. It's just important to know that the coefficient is the constant of variation, and then the power could be any value. This might help you remember where you've seen this stuff before, because we say that y varies as the 8th power of a, or that it is proportional with the 8th power of x, excuse me, not a. Proportional, or that it varies with. So we did this in Honors Algebra 2 with direct and inverse variation. In Honors Algebra 2, we used y equals kx and y equals k over x. This was direct, and this was inverse variation. It's basically the same thing, except now this year we're going to say x to the negative first. But we're also going to say that really this exponent here could be anything. Okay, as long as this is a positive number here in that exponent, we're going to say it's directly proportional. As long as this is a negative exponent, we're going to say that it's inversely proportional. So as we move on here, a being positive means that we're dealing with a direct variation, or that f of x varies directly with the 8th power of x, whatever a is. If a is negative, then it varies inversely with the 8th power of x. So we're going to determine if these are power functions, and then we'll describe what x and a are. This is a power function here. Sorry about that. This is a power function. K is -3, a is 4, and we would say that y varies y varies directly with the 4th power of x. Y varies directly with the 4th power of x. This, or f of x, varies directly with the 4th power of x. All right, if we simplify what we see in part B, cube root of 8 is 2, and then we can rewrite the cube root of x to the 5th as x to the 5/3. Remember, rational exponents, the numerator is the power, the denominator is the root. So this is a power function. K is 2, a is 5/3. This is positive, so this is still a direct variation. We would say that f of x varies inversely. I messed it up again. F of x varies directly with the 5/3 power of x. All right, this next one here, 7 times 2 to the x, that's an exponential. Okay, base is 2, so it's growth, but it's not a power function. And then our last one here is a power. Now this one would be inverse because of the negative. So we would say that h of x varies inversely with the 5th power of x. H of x varies inversely with the 5th power of x. With the 5th power of x. The negative is where the word inverse comes into play. We don't have to say that it varies directly with the negative 5th. It's just it varies inversely with the 5th power of x. Sorry about that. All right, let's take a look at the next example there. The volume V of a sphere varies directly as the cube of the radius r. And the radius of a sphere is 6. The volume is 904.779. What they've done here is they've given us a complete pair of values with the 6 and the 904.779. We have both the radius and the volume. So we can actually use those to find the k value. Let's start by interpreting what this says. V varies directly as the cube of r. V varies directly as the cube of r. So V equals some constant of variation k times r cubed. If it would have said inversely there, then it would have been -3. But it didn't, so it's +3. And now we can use our values 6 and 904.779 in order to find k. So I know that k is going to equal v over r cubed, and then I can use that volume that I have, 904.779 divided by 6 cubed, and we can get an approximation for k, which is 4.189, 189. That's our constant variation. It has no units. So the other thing I'm going to do is, since as I read on here it says, what is the radius of a sphere? We want to solve this thing for r. So r is going to be equal to, if I divide by k and then take the cubed root of volume divided by our constant variation. Now I know we have a value for our constant variation, but I'm just going to plug that in when I plug my new volume in. Okay, I'm going to rewrite this using rational exponents. R equals v over k to the 1/3. Just a reminder that cubed root is to the 1/3. And now we're going to put in the value that we were given for volume to find the new radius, 268.083. And then I'm going to divide that by the 4.189. And really what I would use is what's stored in my calculator. Let's see how long this takes to open up here. When you take this then to the 1/3, you could type this all in at one time. When you take this to the 1/3, you're going to get about 4, it's just almost exactly 4 centimeters. It's like 4.000, a couple more zeros, and then a 3. So we'll just say about, rounding to the thousandth, 4.000 centimeters. See if that pops up. Okay, next one. Force of gravity on an object is inversely proportional to the square of the distance from the center of the Earth. So I'm just going to highlight the important parts here for writing our equation. F is inversely proportional to the square of d. So inversely means it can be a negative exponent. So F equals some constant variation k times the distance to the -2nd. Put that over a little bit so we can see that negative exponent d to the -2nd. That's it. Write an equation that models this situation. That's it. All right, and the next one here, they want us to do some regression. This is a power regression, so it's the same thing that we've done in class before with regression. Instead of linear or quadratic, it's just power regression now. So we want to put these lists into our calc, into list 1 and list 2. Just clearing these out here quick. So we have 1.0, 1.5, 2.0, 2.5, and 3. And 7.95, 3.53. Lost my, try that again. Oh, this thing's being all sorts of fun right now. 7.95. There we go. 3.53. 2.01. 1.27. And zero point 0.9. Just do a quick scan to make sure you got them in there right. Normally I'd look at a scatter plot. They're just telling us to do power regression, so let's go ahead and do that. So we want number, oops, sorry about that. So we want number, I think it's 0. Let's go down and find out though for sure. Oh, nope, that's exponential. We want A there, power regression. List 1, list 2, you know the drill. And to be honest, it really doesn't matter. I know this goes against everything we've done for 2 years, but we didn't look at a scatter plot. We're not plotting the line of best fit. So unless if they're asking us to find a value later on, you don't really need to put an equation there. Let's check if they are asking us. Oh yeah, look at part C, use the regression model. So we might as well put in y sub 1 there, alpha trace 1. Okay, we can go the old vars function, y variables method. But we're ready to go here to calculate. There's our power regression there. Use that to write our equation here. Y equals A is our constant variation, 7.931. I'm just gonna get as much as I can see on here, times x. Well, hold on. Let's use some useful variables here. How about I for intensity, and we're talking distance. So distance taken to the negative, so it's an inverse variation, negative 1.98746,764. Right, now that we have this stored, we can use it to predict the intensity of an object that's 2.75 meters away. So we're going to find I of 2.75, and we'll just type that in right away. So remember, it's stored on our calculator as y sub 1, so we can go alpha trace, grab that y sub 1, and in parentheses, so it's going to put that value in for x. We put 2.75, and we come up with 1.062. We're talking intensity here, so we are in watts per square meters. Okay, on the back side of this sheet, so the front side was mostly applications of power functions. Now we're going to look at their graphs specifically. In class, if we have some time, we'll use Desmos to illustrate this a little bit more. But we're just going to talk about what we know about even and odd functions. Make sure you understand what we're talking about here. Y equals x to the a. So a is the exponent. So if you have an even function where a is greater than 1, that would be something like y equals x squared, y equals x to the 4th. We know the end behavior is going to look something like this, or the graph is going to look something like that. Okay? I'm just going to throw some axes in here, because we're only talking about one term, so it's going to go through the origin. If a is less than 0, but is even, so something like, oh, I don't know. Let's take a look at a graph here. Y equals x to the negative second. Let's take a look at what that looks like. Oh, so from our graph from class here, so we'll go a standard zoom. What we're going to see is this thing looks something like this. So that was terrible. And it's going to continue to look like that even if we did x to the negative fourth, x to the negative sixth. They're just going to get tighter and tighter to that origin there. If a is between 0 and 1, well, that would be something like 1/2. So we can put some of these as examples. A to the 1/2, a to the negative second. This was a squared that we used kind of as an example there. If it were a to the 1/2, that's a square root function. We get something like that. All right, now let's talk about odd functions. Odd functions, if you have a greater than 1, you're talking about something like a cubed as an example, a to the 5th. We know what those look like. If it's less than 0, something like a to the, how about even a to the negative first? That would just be this. And if a is between 0 and 1 but is odd, like a to the 1/3, a cube root function. Did those in Algebra 2 as well. We did those in the same chapter we did the square root function. Okay, so we kind of took care of this. We just wrote out what we would expect in general from these sorts of what we'd expect from the graphs given an even or an odd, and if it is greater than 1, less than 1, in between 0, or less than 0. And we're going to use that to help identify these graphs in this example down here. So I'm going to write down here y equals k times x to the a as just a reminder. Okay. Think about what the k value is going to do. If that's negative, it's going to flip the graph upside down. So we didn't have a k value in this thing that we had up here. So if we would have taken any of these and put a negative out in front, it would have flipped them, right? Vertical flip. Okay, if we would have done a negative here, you don't have to go back up and draw these, but we would have put these down here like this, okay? So that negative would flip it. So down here, we know that everything that's up above this x-axis is a k value that is greater than 0, and everything that's below the x-axis is a k value that's less than 0. Now let's start identifying what's happening in these different lines here just in that first quadrant. Okay, look at the line represented by curve C. It's just a linear function. So we know that as we look at this, a must equal 1. If you look at B, if you look at this curve here, B, actually, I'm going to use a little bit brighter color. There we go. There's B, which is also reflected down here. We know that A must be greater than 1. Okay, that could be something like a cubic or a quadratic, quartic. Okay, it doesn't matter if it's odd or even because it's going to do the same thing in the first quadrant. If it were cubic, it would do this thing. If it were quartic, it would do this thing. Okay, but we're just looking at that first quadrant there. So we have a being greater than 1. Here we know also a is greater than 1. It's just that k is less than 0, so it's flipped it upside down. I suppose we could also put that this is an a equals 1 with h right there. So here was a up here, I'm sorry, C, line C, and then line h down there. Both have a values that are 1. I see curve D kind of reminds me of that square root function that we had. And so does its counterpart down here, G. So in both of these, we know that A is between 0 and 1. Maybe it's a square root, maybe it's a cube root, but it could be any value between 0 and 1. And then the last one that we have, curve A or curve J, must be an A value that is less than 0 because it's creating an inverse graph, the reciprocal graph. Okay, so we can use those the pieces of information we just worked on to help us answer these questions over on the left here to help match these with what graph they are. So as I look over here, why do we identify? Oh, we'll just go down the list here. So this is an even. Well, I suppose that doesn't matter, but it's a negative a value, or excuse me, negative k value out in front. Negative k value. So I'm looking down below, and it's got the quartic. So it's a value that's greater than 1. So that must be that blue one that I have drawn right there. So that is I. The next one is positive, so I know I'm looking up in the first quadrant. X to the negative fifth means that the negative, I'm going to have some sort of reciprocal graph, so I'm dealing with graph A, curve A. Because, oops, I didn't write it up here, A is less than 0 for that one. All right, 2x to the 1/4, it's positive. X to the 1/4 is a fourth root graph, so it's going to look like the red one that we have up in that first quadrant. Looks like we're going to have a repeat here because I see another negative and a value that's bigger than 1, so that's just like I. So that is going to be the same thing as the first example that we had. Don't be fooled by the 5/3. It's a value bigger than 1. That does not mean it's a just because it's a fraction doesn't mean it's going to be like a cubed root graph. This is a value that's bigger than 1. So it fits into that same category as that one in terms of the first quadrant. It's going to be I lost my I here. Well, except we're in the fourth quadrant for this one. So it's going to be like this one, A greater than 1. So we have negative, so I'm looking in the fourth quadrant. Negative 2 less than 0 is going to be this guy here, which is graph J. And then 1.7x to the 2/3. Okay, so positive, looking in the first quadrant, to the 2/3 would be between 0 and 1, so we're looking at graph D. So I think this is the most important thing I'd like you to get out of this, is what these graphs look like. And they do have something like that in your textbook too. If you just jump right into identifying what those are, I think that's tough. I think if you actually piece apart what the A value is doing, what the K value is doing, it makes these problems a little bit easier.